The next topic of discussion for today's is the Gauss-Markov theorem. See, an estimator like the beta hat which we had over here, an estimator must have some properties, and only when it satisfies those properties of a so-called good estimator, we are going to accept it. The two important properties are that the estimator should be unbiased and it must have minimum variance. So Gauss-Markov theorem is all about the properties of least squares method. So the characteristic of linear unbiased estimator, which is here referred to as BLUE. BLUE stands for best linear unbiased estimator. So with the help of this Gauss-Markov theorem, we will be proving that, and this Gauss-Markov theorem states that given the assumptions of the classical linear regression model, the estimators alpha and beta are the best in the class of linear unbiased estimates. So to prove that beta hat is blue, we basically have to prove three things. First, it is linear. Second, it is unbiased. And third, it has the minimum variance. Now, we go for the first one. Let us try to prove that my beta hat is a linear estimator. Now, we know the formula for beta hat. In the deviation terms, it is equal to beta hat summation small xi yi divided by summation xi square. And if we write it in the form of a non-deviation form, then it will be beta hat is equal to summation x minus x bar y minus y bar divided by summation x minus x bar whole square. Now, we assume just that this wi, we assume that this wi is nothing but xi divided by wxi whole square. So we can write the first equation as the first term, this term as in this format, that is beta hat is equal to summation wi yi. The next thing which we do is we add summation on both the sides. Means we have this wi, we summation over here, so it becomes summation wi is equal to summation xi divided by summation xi square. Now, this xi is nothing but xi minus x bar. This xi is nothing but xi minus x bar. So this we can, when we do the summation of it, we can write it as summation xi is equal to summation bracket open xi minus x bar. We know that summation xi is equal to 0. So when summation xi is equal to 0 in this term, summation wi, when this is equal to 0, the entire term becomes 0. Next, we know that yi, that is in the small yi, that is in the deviation format, is equal to capital Yi minus y bar. Here again we multiply both the sides by wi. So we get summation small wi is equal to summation wi bracket open yi capital Yi minus y bar. Now we open this summation, open this bracket. So what we get is summation wi small yi is equal to summation wi capital Yi minus y bar capital Y bar summation wi. So now summation wi we have seen in our previous discussion is equal to 0. We have just now proved it over here. Summation yi, we have just now proved that summation yi is equal to 0. So this term summation yi, this term disappears, this term becomes 0, so this term disappears. So we are left with wi yi is equal to summation wi yi. So this we can say that summation wi yi is equal to beta hat. Now, our regression model, it can be defined as yi is equal to alpha plus beta hat xi plus ui. Now, beta hat, just now we have proved that beta hat is equal to summation wi capital yi. Now, what we will do, we will use this yi, we put it over here, so we get the equation beta hat is equal to summation wi under bracket alpha plus beta xi plus ui. We open the bracket and we get the final term, which is equal to beta hat is equal to alpha summation wi plus beta summation wi capital xi plus summation wi ui. Now this equation is linear. As this equation is linear, that is, there is no square term or cubic term in any one of the variables or the parameters. So this is a linear equation. Hence, we have proved the first thing, that beta hat is a linear estimator. Now, the next thing which we will try to prove is that beta hat is an unbiased estimator. What we have over here is yi is equal to our regression equation, beta xi plus ui. Beta, we know the formula for beta is equal to summation small xi yi divided by summation xi square. We have assumed wi to be small xi divided by summation xi square. We take the summation of this on both the sides. So in the top it becomes summation small xi is equal to 0. So wi is equal to 0. Now we have beta hat is equal to summation wi yi. Beta hat we can open. When we open, we get the final equation beta hat is equal to alpha summation wi minus beta summation wi capital xi plus summation wi ui. Now we introduce this. Summation wi is equal to, we have it over here, summation wi is equal to summation xi divided by summation x square, and we multiply x on both the sides. See, we multiply x on both the sides. So what we get is summation wi xi is equal to summation xi. Now we multiply it by xi. So this term we have multiplied over here, and also we have multiplied over here. Now because this term, the first xi term, is in deviation form. So we open it up. So it becomes summation capital xi minus x bar multiplied by this xi divided by the same, which was earlier the same term, summation small xi square. So now we again cross multiply and open the bracket. So it becomes summation xi square minus x bar xi. This divided by summation xi square. Now summation xi square, what is below, we can open it. We see some small x is equal to x minus x bar. So we write it as summation xi square is equal to, we write it, and then when we do the square, we put an, if this is the square over here, we put a square over here, it is summation. So this is equal to, now we have this a minus b formula. A minus b whole square is equal to a square minus 2ab plus b square. So we write it, we in the same terms, x square minus 2 xi x bar plus x bar square. Now this we can write it as, because we have a summation sign, we open the summation sign and introduce it within each of their terms. So we become summation xi square minus 2x bar summation xi plus n, because x bar is a constant, n x bar square. Now this n can be opened up like this. There are two x bars, so one x bar we open. So once we open one x bar, now it is, we can minus this term from this term. So what we finally have is summation small xi square is equal to summation xi square, this term, and this one is gone. So we have x bar summation. See, this n cancels. So what is this, and this term is the same. This is 2x bar summation x. This is x bar summation x. So here there is two terms. Here there is one term. So one is minus. So what we finally get? So means this comes as it is down. So this is the summation xi whole square in the deviation form. Now we do another thing. We have this summation xi wi xi, this we can write it as summation xi square minus x bar xi divided by summation xi square, and summation xi square we have just now seen, we can write it in this format, that is summation small x square is equal to capital X square minus x bar summation xi. Now wi xi, the summation of it, above it is summation x square minus x bar summation x square, and beneath also, beneath we have this term. So these two terms are same. So when these two terms are same, this is equal to 1. So we have beta hat is equal to alpha summation wi plus beta hat summation wi small xi plus summation wi yi. Now here wi is summation wi is equal to 0, alpha is a constant, and summation wi xi we have just now proved is equal to 1. We put all these things over here. So alpha multiplied by 0, this will vanish. So beta multiplied by summation wi xi, this is equal to 1. We have just now seen over here. So this is equal to 1. And what is this term? This term comes as it is. Now, so we can say that beta hat is equal to, okay, we can say that beta hat is equal to beta plus summation wi ui. Now this beta term, we take it over here, and when it goes to the left hand side, it becomes minus. So beta hat minus beta is equal to summation wi ui. Now we take the expected value. Expected value of beta is equal to beta, because expected value of beta will be beta, plus expected value of summation wi ui. So we can write that expected value of beta is equal to beta plus summation wi expected value of ui. We just rearrange the terms, and if you remember our assumptions of the classical linear regression model, the assumption says that expected value of beta hat, the assumption says that expected value of ui is equal to 0. So when this term becomes 0, this entire terms it becomes 0. So expected value of beta hat is equal to beta. So when we are saying that expected value of beta is equal to beta, this proves that beta hat is an unbiased estimator. We stop over here.